Hello, it's me, and I've had a lot of people ask me regarding the formulation of algorithms. How do you find the pattern to help solve a puzzle? And when you have a wide variety of different puzzles, a lot of times you can make correlations from one to the next, but from time to time you end up in a situation where you don't have anything that you've dealt with before, and you're kind of in a position where you have to figure things out as to how to solve a problem. In which case you have to know how to design a series of instructions or an algorithm so that you could best solve a puzzle. Because sometimes there's tutorials out there and sometimes there isn't. So you want to be able to do that. The next step that I'd like to do when describing puzzles, now that we've gone through a series of different solves and a series of different algorithms that can be applied and reapplied and minorly adjusted, I'd like to get into the notion of how you can maybe design your own so that you can solve whatever puzzle comes at you. First, let's talk about what an algorithm is. What exactly do we mean by that? What's an algorithm? What's a commutator? Not being steeped in math and not going to go into details like that, I'm just going to describe it very simply that an algorithm is a set of instructions. And with that set of instructions is you have a specific goal. And that goal is to put the cube, or the puzzle rather, from some initial configuration to some sort of a final configuration, something that is more than just by random chance. So it's a series of instructions in order to do that. A commutator is a specific subset of an algorithm, a type of algorithm that has a form that allows you to, with a series of moves, put the puzzle back to the configuration that it was, save for a couple of pieces. So it's a way of moving one piece around the puzzle and not affecting everything else, because what you're doing is you're deconstructing the puzzle, making some sort of a move, and then reconstructing the puzzle. We've seen this when we were doing the megaminx. In order to do the 3-cycle commutator that we were doing to get the middle triangles, we had to do setup steps of deconstructing the cube, or the puzzle rather, doing our commutator, and then putting it back. That whole thing is basically an algorithm, not something, and the only part that you memorized was the commutator in between that had very specific moves that caused a little bit of movement of each individual component, but then you got it back. That's part of your algorithm too, which you kind of made up as you went along. To demonstrate that, I'd like to do it with this nice simple Skewb puzzle to see how it is we can generate an algorithm when you're confronted with something like this. The reason that I'm using this is, number one, it's simple to illustrate the point, and number two, I wanted to see if we can design something new that hasn't exactly been seen, despite the fact that there are other tutorials that are out there. Let's see what we can get with this. So the first step when being confronted with a puzzle like this Skewb here, cute little puzzle, is to see first off what it is. What are our faces? What are the different components? How does it move? Can we correlate this with something that we already have? Now, although this is a cube much like a Rubik's Cube, you can tell immediately that it doesn't move like that. It actually moves a little bit more like a pyraminx, almost like it was something that was taken from a pyramidal form and sort of put into a cubic form, moving quite the same way. As a matter of fact, initially, I believe Meffert invented this or something like this, I hope I have the history right, and originally called this the cubic pyraminx to launch the whole pyraminx line, but then was later called a Skewb. And it actually moves very much like a pyraminx, where we're swapping corners like that. What we can define is we can maybe define this as a side, but something that jumps out with this is that it's not a face turner. In other words, it doesn't turn by the face, it turns through the vertex, which is a slice right through the corners actually. So you can see that I'd like to define this as a face, but there's just too much going on here. It's hard to define it as such because I can turn it from here, but then another turn slices right through the original face. So because of that, it has its own way of turning, which is maybe more like a pyramidal type puzzle put into a cubic form. Once you've defined how it turns, and once you've defined what you're going to call your side, say we'll call this our middle, we'll call these our edges over here, then you can try to generate a series of movements that will deconstruct, reconstruct, and then you can see how it moves everything around. So it's very apparent that with this simple puzzle, it only moves in a couple of planes. It moves here, and it moves here, it moves here, and it moves here. Now, I'm not, like I say, going to get steeped in math, nor am I going to get steeped in annotation. Much like with the square one tutorial, I find that oftentimes that serves to confuse, and it's good if you want to memorize a whole bunch of things to solve it quickly, but it doesn't really help in terms of puzzle solving because you can very easily forget what you just memorized. So I'm going to define what movements are available to me, and this sort of has a crisscross movement, much like much like the pyramids. What we're going to try to do is from that movement generate a commutator, generate some sort of an overall algorithm, see how it moves things around this cube, and then apply that for the purposes of solving this, so that maybe we can do that in other ways with other puzzles. So what I would do is do a very simple commutator of deconstructing and reconstructing, and it usually takes the form of A, B, A prime, B prime. So things like FRU, RIUI, FI, that's a commutator, giving an overall series of instructions or an algorithm that allows, say, edges to flip while everything else remains the same. Or URF, UU, FRU. That's another example. So in deconstructing, what I'm going to do is I'm just going to move this down, paying very close attention. We'll put the green on the bottom, and we'll move this down here from the right side, from the top. I'm just going to define this as a counterclockwise motion and this as a clockwise motion. So we're going to go down, starting with counterclockwise. So down counterclockwise, down clockwise, up counterclockwise, up and deconstruct it. So let's see what happened when we did that. Something that stands out is this didn't change. This wasn't touched. Green stayed the same. All of these stayed the same. So this center and these corners didn't get touched at all. So let's look at what happened with the middle here. What happened with that is that the purple middle went up here, and the blue, which was here, came down here. So now I know these got swapped. The back stayed exactly the same, didn't get touched. And this, well, let's see, this was silver here. So this was transferred to here. This yellow one was transferred to here. So now I know that. Now I know that that very simple commutator kept everything here the same. These two got swapped, and these two got swapped. So that's how I kind of come up with how things will move around the puzzle. What about these guys here? Well, that might be a little bit more complicated, but let's see what happens. A true algorithm, if applied enough times, will return you back to the original state of the cube. So let's do it again and see what happens. Down, down, oops, up, up. And as you can see, we've returned all of these back. So green is in here, my purple is here, my blue's back up here, yellow and yellow. So by doing it once, it flipped it. By doing it twice, it flipped it back. Once again, these guys aren't touched. These guys still aren't quite where it needs to be. So there's some sort of a rotation there. Let's do it again. Turn, turn, turn. Predictably, these swapped the same way. These two got swapped, but these two got rotated. But these guys all got rotated back into configuration. Keep going. So just bear in mind that this was the third set. The first one swapped these two. Second one put it back. Third one swapped them again, but put these guys back. Here's the fourth one. Down, down, up, up. Now doing our fifth one. Down, down, up, up. Once again, these are swapped. And we'll do it once more. Down, down, up, up. By the sixth one, we're back to where we started. So we know that from the crisscross commutator that we're developing, these two get flipped, these two get flipped, these two stay the same, and by the sixth one, we go back to our original conformation. That's the full algorithm. Now let's see what happens with these guys up here, because that's going to be useful. So let's do it once, and let's pay attention to the fact that these purples are here. So down, down, up, up, bearing in mind that we started off with an up, right, counterclockwise turn. So I know that purples came from here. I know that these are the same. This purple here rotated. It went from here Yeah, actually, yeah. So it was blue up top here. This blue one down here was purple. This rotated. This little thing here rotated counterclockwise. It rotated the same direction. It's almost like a fractile sort of a thing where the small components rotated the same way that the large components. How about this guy? Well, this also rotated counterclockwise. It was yellow here, then it came here. This purple that was here came up to here. So this rotated counterclockwise, this rotated counterclockwise. These didn't do a thing. How about here? Well, this was yellow. Oops, I'm sorry. This was silver. Silver went up here. So from this standpoint, it rotated clockwise. If I were to hold it here, this is a clockwise rotation. So here, this rotated like this. So this was counterclockwise, and this here, well, from this perspective, I suppose, would be counterclockwise, but from this perspective, clockwise. So it followed the same pattern as these, and this also, from this standpoint, was also a counterclockwise roll, but clockwise from this standpoint. So everything was counterclockwise when holding here. So now we can make some predictions based on this commutator. It rotated counterclockwise once. So my prediction, if I do this again, rotate it here, what I'm going to have is the purple one is going to be up here, the yellow one is going to be up here. Turn, 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 and indeed the purple one is here, yellow one is here. So I've generated an algorithm. I've generated a limited number of moves that have a predictable result. And of course these things were flipped back. What we are going to do now is let's apply this known commutator, this known algorithm, to this puzzle and see if we can come about some sort of a solve. So why don't we scramble and see what we can do. Abracadabra. Okay, so let's see what we got. We'll start off with the green. I just by convention tend to do that. The very first part of the solve, as we've defined this that goes right through the axis, being a skewb and all, is to just try to get things set up, because now I know how to move these pieces around, but I've got to get them set up right. So I want to move this up into here, so I'll just take any avenue that I can. There. So I've got the green here. What I want to do now is I want to move another greeny yellow one over here, so there's this. Doesn't move quite in here. Now I can just sort of force it and make it go around, but when I put it in here, I know that there's a way that I can rotate this. But I can't rotate it next to this guy because I'm going to cause this to rotate too. So I'm going to put this over here. Now if I were just to test out my algorithm, although I could try to just permute this around and see what it does. If I wanted to rotate this, I want this green, whoops, try that again. I want this green, it does that sometimes. I want this green to come where this yellow is. I want it to come over to here, which means I want a good clockwise rotation. So if I do my algorithm, starting off with clockwise rotation, which is here, I should be able to do that. It'll flip these guys, but who cares? These are going to remain the same. So down, down, up, up. I didn't have to move it up, but it did rotate it because it was already down there. So there it is. Bang, that's where I want it to be. Now, of course, I didn't have to do that. I just wanted to demonstrate. So how about the green and pink? Here's a green and pink. I could do it the same way, but yeah, for the sake of testing our algorithm out, as this comes here, I want this green to be where the silver is. So this green to come down here. This is going to be a clockwise rotation. So let's do that. Down, down, up, up. It rotated there, so I just rotate it down, and there it is over here. Finally, I've got this. This is rotated wrong. So I'm going to keep applying this commutator that we've discovered. Put this over here, and I want this to rotate where the purple one is. So to rotate this here, this is a clockwise rotation. So in the true spirit of a fractile, let's rotate the larger block in a clockwise rotation so that the smaller block can go clockwise. So this is clockwise, down, down, up, up. Well, I didn't have to move it up, there it is. So this constitutes our first side using our commutators, using our algorithm. Not too shabby. The next step is we want to get our, quote, cross. And to do that, I want to move these middles into place. So this is where the fun of the puzzle solving is, because to know a commutator is only step one. Step two is to apply it by putting things into position based on strategy. Doesn't take much to learn and memorize commutators and algorithms, but the strategy is really what's important. So let's see where things are supposed to go. This silver one should be in here. Is there any one that's already in? No. So I want to put the silver one over here, and it's already 180 degrees, and I know how I'm going to do that. I know how I'm going to place that. For simplicity's sake, let's just place this down over here. And if I apply the algorithm, I'm going to flip-flop these two and flip these two as well. And this is going to stay the same. So down, down, up, up. All right, so there's the blue one over here. Let's take a look around. This is in place, this is in place. What I'm going to do is this. What this algorithm does is it flips these guys, and keeps them the same. So now that I know where this is, I'm going to find the one that's just opposite that, because if I hold it here, I'm just going to keep flip-flopping these guys and see if I can commute these into place. So it's just opposite of the purple is going to be the pink. So I want to get the pink opposite the purple. Well, how am I going to do that? Well, here's the pink up here, and if I put this pink down here, it'll be opposite, and this won't change. So these two will always be opposite here. So that's what I'm going to do. Down, down, up, up. Pink is in here, purple is in here. These two are cool. Now what about these guys? So now I know if I apply the algorithm that we came up with, these two will always be within one move of getting back where it's supposed to be. These guys can move up and down. So what I can do is I can move this down to here, this up to here. This will be solved. These will be exchanged. But I know that if I turn it back here, this will stay and will not move. These two will exchange back, and the silver that I put up here, I can now put down here. So that's the strategy part. And then it's just a matter of carrying it out. Down, down, up, up. As promised, this is in place. These are within 180 degrees of each other. I use this a lot during my Megaminx solves, or my Supercube solves, of getting things within 180 degrees after developing an algorithm that'll flip those. So what I'm going to do now is turn it this way. If I do that same crisscross algorithm, these two will flip back into place, these two will exchange, and this will stay the same. So all my centers will be solved. So down, down, up, up. And thus is the power of strategy. So all of these centers are in place. So speaking of strategy, how can we use our new algorithm to float these guys back into place? Well, I know that I can, as long as I do a series of 2 with those algorithms, these will flip and then flip back, these will flip and then flip back. And with each turn of that, I know I can predictably rotate all of these. Now I know immediately there's a problem because 2 are in and 2 are out. So no matter what I do, if I keep flipping them around and I don't change things around or use strategy, I'm not going to be able to get them all in place. I want them all out of place so that I can put them back into sync. So if I turn this counterclockwise, this will be in place, but this will be out of place. This will be out of place, and this will most likely be in place because they're sort of tied to each other. Yeah, this will rotate over here. So instead what I'm going to do is I'd like to rotate it to where this ends up here. So this will still be out of place. This will be out of place, so will everything else. So how are we going to do that? Well, I can rotate it clockwise, counterclockwise once. But if I do that, my centers are going to be mixed up. So I have to do a move that's going to be 2 moves so that I can get back my centers here. So 1, 2. If I move it twice clockwise, this will be out, of course, as will these. So I'm going to do my commutator twice in a clockwise fashion. So 1, 1, 1, 1, 2, 2, 2, 2. These are back, and all of these are out of sync, which is exactly what I wanted to do. Now, because these are here, they have to move in opposite directions. So I know that that's not going to work. Move this here and it'll be fixed. Move this as this moves counterclockwise, this counterclockwise, it'll take 2 to do that. So because this is out of sync, and because the geometry of this is fairly straightforward, I'm going to rotate it to this side and see what happens. One clockwise move will put this in place. The same clockwise move will put this back in place. But I have to do 2 moves. So why don't I do, because this is 3, 2 counterclockwise moves. 1, 2, this will be back in place. 1, 2, this will be back in place. And these will predictably go out and then back in. So it's going to be counterclockwise, like this. Twice should fix the entire puzzle. So 1, 1, 1, 1, 2, 2, 2, 2, and you've done it. So you've generated an algorithm, generated a commutator, and as such was able to solve this, and you can do it over and over and over again without any problems. All right, let's do that again. Just since we've generated a novel solution to this, or maybe it's not novel, maybe it's done, I honestly don't know, but maybe we got lucky. Let's see what happens. Well, here's a green and yellow. Find the other green and yellow, just kind of put that in. Here's the other green and yellow here. Can we easily put it in? Well, we want to put it here, but we want the green one to be where the yellow one is supposed to be here. So we want to rotate this in a counterclockwise. So boom, 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 down. There it is. Green and pink. All right, counterclockwise. So boom, boom. So there that is. That's fine. In a counterclockwise rotation as well. Down, up, and that is. So we've got our side over here. Everything seems to be in place except here, but let's just kind of focus, eyes on the prize. Move this down to here. Up, up. We've got this here. What's just opposite the yellow? Gray. It's already in place. So because these are already in place, I just have to fiddle with these guys. So this will come down here, which is good. Then the pink will come here. Rotating these 2. Sorry, once to flip-flop these guys. Down, up, up. This is in place. This goes behind us, as that's not going to be touched by this algorithm. The application next will rotate these 2 and rotate these 2. Down, down, up, up. And there you have it. These are all in. We just have to get these guys in. So this is going to be a clockwise rotation. 1, 1, 1. 2, 2, 2, 2. That's what I wanted. These 2 are too similar to each other, so we've got to skew it like this. This is going to be a counterclockwise rotation, which is over here. 1, 1, 1, 1, 2, 2, 2, 2, and done. We did it. So that's a very simple approach to a very simple version of the puzzle. And how we use commutators.